Welcome to this explainer for course DPEI 803, Part 4, Physics. Today, we're going to break down the absolute fundamentals of how things move. We're zeroing in on the kinematics of linear motion. You know, whether you're watching a charging elephant, a soaring eagle, or honestly just sitting there looking straight ahead right now, motion is literally everywhere. But before we can wrap our heads around the complex, invisible forces governing the entire universe, we've got to start with the basic rules. So here's our roadmap for today's explainer. We're going to cover the language of motion, rest, motion, and relativity, the three types of motion, vectors versus scalars, distance, displacement, and speed, and finally we'll wrap up with velocity and acceleration. Let's get right into it. First up on the agenda, the language of motion. We're talking about kinematics. Now, that word actually derives from the Greek word kinema, which simply means motion. You can think of kinematics as essentially the what of movement. It gives us the specific language and the mathematical tools we need to describe motion perfectly. And we do this before we ever even have to ask why an object is moving in the first place. It is absolutely crucial. It's the groundwork for literally everything else we're going to do in physics. All right, moving on to our second topic. Rest, motion, and relativity. How do we actually establish if an object is moving at all? Well, picture a motorcyclist stopped on a road. If a body doesn't change its position with respect to its surroundings, like the nearby buildings or a tree right next to the road, it's considered to be at rest. But the second that motorcyclist revs the engine and continuously changes position relative to those exact same surroundings, well then they are officially in motion. Makes sense, right? But here is the real kicker. Motion is entirely relative. It all depends on your frame of reference. Imagine a passenger just chilling, sitting on a moving train. To the person sitting right next to them, they are perfectly at rest. They aren't going anywhere. But to someone standing outside on the station platform watching that train zoom by, that exact same passenger is in rapid motion. So you see, there's no absolute state of motion. It totally depends on where you're observing from. Okay, let's jump into our third area. The three types of motion. Pretty much everything moving around us in the physical world falls into one of three distinct categories. We have translatory motion, rotatory motion, and vibratory motion. So let's break down exactly what these look like in everyday life. Now, what's super interesting here is translatory motion, which is when a body moves uniformly in the exact same direction. But it actually breaks down even further. It could be a linear, straight-line path, kind of like a train cruising down its tracks. It could be random, irregular motion, just like a bee buzzing unpredictably from flower to flower. Or it could even be circular motion, following the path of a circle, exactly like the cart swinging around on a giant Ferris wheel. Meanwhile, let's check out the other two types. Rotatory motion is when every point of a body spins around a fixed axis. Just think of a ceiling fan in your living room or the drum of your washing machine. It spins like crazy, but the axis itself stays firmly put. Vibratory motion, on the other hand, is a repeating to and fro movement around a fixed center position. The absolute classic example of this, a child swinging back and forth on a playground swing. Actually, let me pause for a second and ask you a quick question. If you jump in your car and drive 20 miles north, and your friend drives 20 miles south, did you both do the exact same thing? Just think about that. This question perfectly sets up our next major leap in understanding physics, which is the absolute importance of direction. Which brings us to our fourth topic, vectors versus scalars. Okay, here is the golden rule you need to remember. A scalar quantity is fully described by its magnitude, and by magnitude, I just mean a number. Things like mass or the number of words in a textbook, those are scalars. You'd never say a truck weighs 10 tons north. That doesn't make any sense. But a vector quantity requires both magnitude and a specific direction. So when you're in doubt on an exam, just ask yourself if the quantity comes with a direction. If it doesn't, boom, it's a scalar. But if direction really matters to the description, you've got yourself a vector. All right, let's move on to our fifth section, distance, displacement, and speed. Let's actually apply this new scalar versus vector rule to measure movement. Imagine you're looking at a map showing a car taking a road trip from Lahore to Multan. Now that long, winding, curved path the car actually has to drive to get there, that is the distance. But if you draw a direct, straight line arrow pointing exactly from point A to point B, that straight, unbending line is the displacement. I'm telling you, this distinction right here is an absolute favorite for exams. Distance is simply the length of the actual path you traveled. It's a scalar quantity. It just tells you how much ground you covered overall. Displacement, however, is a vector. It's the shortest possible distance between your initial and final positions combined with the specific direction you moved. Basically, distance is how far you went, but displacement is how far out of place you are, complete with a precise direction. Now, to figure out how fast you actually cover that distance, we calculate speed. Speed is just the distance covered by an object in a given unit of time. And because it relies entirely on distance, which remember we just learned is a scalar, speed is also a scalar quantity. It completely ignores direction. Your car's speedometer is a fantastic everyday example. It simply gives you the instantaneous speed at any given moment, telling you exactly how fast you're moving right then, regardless of whether you're heading north, south, east, or west. And that brings us to our final section, velocity and acceleration. So what happens when we take speed and add a specific direction to it? We get velocity. While speed is just distance over time, velocity is the net displacement over time, which absolutely must include a specific direction. Because velocity is a vector, simply changing your direction changes your velocity. Think about it. If a car is driving on a perfectly circular road at a constant, steady speed, its velocity is actually changing at every single instant. Why? Because its direction is constantly changing. Mind-blowing, right? And honestly, whenever velocity changes, we introduce acceleration. Acceleration is a vector quantity that measures the rate of change of the velocity vector over time. So whether an object is speeding up, slowing down, or literally just altering its direction of travel, we measure that rate of change of velocity as acceleration. Well, we have now officially mastered the language to describe motion. But as this famous law from Isaac Newton hints, an object remains at rest or in motion unless acted upon by a net force. In other words, it actually takes a physical force to cause these changes in velocity that we've just been talking about. And that brings us perfectly to the threshold of dynamics, which is the why of motion. Kinematics is the what, but dynamics gives us the push and the pull. So based on what we've learned today about rest, motion, and velocity, what invisible forces do you think are acting on your body at this very moment to keep you exactly where you are? Think about that for a bit. Thank you so much for joining this explainer. Keep wondering, keep studying, and we'll see you next time.